In this lesson, we're going to finish up looking at nuclear power. We're going to begin by looking at some of the environmental impacts of nuclear fission that we discussed in the last lesson. Then we're going to look at two strange things about nuclear fusion that you may have noticed. We're going to revisit the idea of energy being converted to mass and vice versa. And then we're really going to focus in this one on going through some examples of the calculations you'll be expected to do at Leaving Cert. Using nuclear fission to generate electricity is fairly low on greenhouse gases, but it does produce a lot of other negatives. So some of the environmental impacts of using nuclear fission as a power source. The first one is the radioactive waste that's produced. And we're talking about the fission products here, so the things that uranium and plutonium form when they break apart. And the problem is they can remain radioactive for a very long time. These radioactive waste can have half-lives of tens of thousands of years, so it's a massive problem, especially for future generations. This is kind of a silly picture of it. No one really leaves massive barrels of radioactive waste lying around the field, but it is definitely a problem. Like some people say, oh, can we just launch them into space? But if something went wrong during the launch, you got radioactive waste scattered all over the planet. So wherever we put it, it's going to cause problems. In addition to the radioactive fission byproducts, there's also the problem of storing the spent fuel rods. So the fuel rods, which were used for fission, will remain radioactive for quite a long time, but also they remain crazy hot. So they have to be stored in these kind of special cooling pools that will do two jobs. One is to cool them down, and they take decades to cool down. They're so hot, they take years and years and years to cool down. And also the water will absorb some of the alpha radiation, so it can be relatively safe. Third kind of environmental impact is containment, so keeping all the radioactive material inside the core where it belongs. And this is the kind of thing where it doesn't go wrong that often, but when it does, it goes very badly wrong. So the big example would be Chernobyl in Pripyat in the 80s, and also more recently the Fukushima Daiichi plant in Japan. Finally, obtaining the ore, so the uranium ore that's used for nuclear fission or plutonium, it itself is problematic. For one thing, they're massive mines, devastating ecological impact, and also for the unfortunates who work there, the obtaining this ore usually also means breathing in radon gas, which we discussed last time, which is itself radioactive. So a lot of these miners are going to develop lung cancer. Fairly grim job. In the last lesson, we looked at some examples of nuclear fusion. And you might have noticed a couple of things that seem strange about how it happens. So to start with, let's go back to the idea of getting them to kind of collide. So let's, for example, here we've got two deuterium nuclei that we're going to smash together to make a helium. And we said that to overcome the repulsion between the positively charged nuclei, you have to really smash them together with crazy amounts of heat. But the question is, why do they then stay there? I mean, if you think they've now got more protons crammed together in the nucleus, why do they not all repel against each other and scatter in all directions? And for that matter, why don't all normal nuclei do that? If you've got all the positively charged protons stuck in the middle. Now the answer, we're going to come back to it in later chapters, this is a very strong force that only works at very short ranges called the strong nuclear force. So if you can overcome the electrostatic repulsion between the positively charged nuclei and manage to smash them together, the strong nuclear force will keep them together. The second thing that you might find a little strange is coming back to that E equals mc squared thing. So the idea of converting energy into mass and mass into energy. So in this example of fusion, you've got two deuterium nuclei, so those two isotopes of hydrogen, smash them together and you get a helium nuclei, and this isotope only has one neutron, and also a neutron that gets kind of bounced off as well. So if you look at that, the mass looks the same, right? You've got a mass of 2 on each deuterium nucleus. Then you've got a mass of 3 on the helium, and you've got that one neutron. So the mass seems to add up. But at first glance, you might think, well, this is a bit of a con. Where has the energy come from? Where has the matter come from that we've converted into the energy here? Now, at first, it might look like it's a bit of a cheat, but it's not. The mass that was converted to make this energy is actually tied up in the nuclei themselves. It's a bit hard to kind of get your head around, and it's a little bit beyond the Leaving Cert, but let's just mention it anyway real quick. Each of these nuclei, the hydrogens that we started with and the helium, they'll each have a certain binding energy. Now, what this means is the energy that you'd have to put in if you wanted to break all these guys apart. While this binding energy isn't shown in the equation that we're looking at here, it is present in all the nuclei that are involved. And in fact, what you find is the binding energy of the two hydrogen nuclei combined is greater than the binding energy of the helium nucleus. So what you've done here is you've released some energy. So that's where it's come from. Just to show it hasn't kind of come from nowhere. Again, it's a little bit beyond the scope of leave insert, but just to not obfuscate anything. So let's again revisit the idea that energy and mass are essentially the same thing, and they can be converted from one to the other. Now, during many types of chemical reactions, this will happen, but it will happen in such small amounts that we couldn't really detect it, even with our most finest sensitive instruments. But with these nuclear reactions that we're talking about, it is noticeable. So like any reaction, you start with something and you end up with something else. And the names for these are the things that react together are called the reactants, and the things you end up with are called the products. In some of these examples we're looking at, the reactants could be just one thing that reacts with itself and splits apart. Or it could be two things combining. Doesn't really matter. There's always a before and an after. And if the mass of what you end up with, the products, is greater than the mass of what you started with, the reactants, then the energy must have come from somewhere. So it's absorbed energy, and vice versa. If the mass is decreased, it means that energy has been released. Okay, so we've been talking about the energy that's released or absorbed by these nuclear reactions, but we haven't really talked about what type of energy that is. And the simple answer is it's kinetic. So it's the kinetic energy that's given to the products, or it's the kinetic energy that's absorbed by the reactants. So let's think of an example to help us solidify this. Let's say that I've got an unstable nucleus, and it's going to decay and give out an alpha particle. And so far we've just been talking about the alpha particle being kind of released or emitted, but it doesn't do justice to just how much kinetic energy is given to the alpha particle. It's violently ejected from the nucleus, it goes flying out. Now what that means, if you think back to momentum, if that alpha particle gets shot off in one direction very fast, that's going to mean that the nucleus is going to move off in the opposite direction. It mightn't move as fast because it's got a lot more mass to move, but it will move. So if we want to remind ourselves about here, we're going to need to consider momentum, and specifically the conservation of momentum. So when momentum is conserved, what that means is whatever momentum you had before the reaction, you're going to have the same momentum afterwards. Here's an example of a quick reminder if you want to pause the video and give this one a shot. And then here's another very similar one, just about calculating the velocity. Remember that momentum has to be conserved here. And then if you're ready up for a challenge, I've got a much more intricate one. This is actually a worked example from your textbook involving also looking at vectors and so what direction resultant vectors take. This would be a good bit of revision. I'd suggest pausing this, give this a whirl, and I've posted a solution afterwards which we can go into in a bit more detail in our class. Okay, so the real crux of this video is we're going to have a look at some of the nuclear energy reactions and the calculations based off of them. And to do that, we're going to need a few tools at our disposal. We're going to need to be able to calculate momentum and how it's conserved. We're going to be able to need to calculate the kinetic energy of particles. And also, we're going to be comfortable with using E equals mc squared, the energy to mass conversion. So we're going to be looking at exercises 31.1. And I'm going to try doing this like we would in class, where I'm going to go through the first two, 1 and 2. Then I'm going to ask you guys to try the next ones, 3 and 4. I've asked you to skip number 5 for now. It's quite involved, and I'll be going into it in a lot more detail in a separate video. It kind of deserves its own separate one. So we're going to do 1 and 2 together. You guys are going to try 3 and 4. We're going to skip 5 and avoid like the plague. Then we're going to look at 6 together here, because it's a bit of a step up. And I'd like you guys to try 7 to 9, and again, avoid 10. So to recap, 1 and 2 together, 3 and 4 yourselves, avoid 5, we'll do 6, and then you guys will do 7 to 9. And as always, I'm going to post the worked solutions up afterwards, but let's give it a whirl first. Okay, here we go. Okay, let's have a look. So we've got 40 litres of petrol is burnt, and it gives out 1.4 by 10 to the power of 9 joules. Okay, and they ask us to find the amount of mass that's been converted into energy. Well, straight away, this 40 litre thing is kind of a red herring. It's just the average carload. We know the energy, that means we can calculate the mass. So let's use E equals mc squared. And we can rearrange that. We know the energy, we're trying to get the mass. So the mass is equal to E divided by c squared. Okay, let's put some numbers in. So the mass is equal to 1.4 by 10 to the power of 9 joules divided by c squared, and we're given the speed of light in the question is 3.00 by 10 to the 8 meters per second. Don't forget that that's squared. Okay, let's put the numbers in real quick. Okay, so what I got? 1.55 recurring, so let's round that up to 6 by 10 to the minus 8. And don't forget our unit here is kilos. All right, so there's number 1. Done. Okay, let's look at question 2. The mass of the sun decreases by 4 times 10 to the power of 6 kilograms every second due to the emission of EM light. Find the energy emitted in 1 hour. Okay, well first off, let's see how much energy that is per second. So let's go with E equals mc squared. And that is equal to 4 times 10 to the 6 kilos multiplied by 3.00 by 10 to the 8 meters per second. And don't forget that that's squared. Now I've ran the numbers already just to speed things up a bit here. And that gave me 3.6 by 10 to the 23 joules. But don't forget that's for 1 second. So to get it for an hour, we times that by 60 to get how much in a minute. And 60 again. And again, I've ran the numbers before. Got 1.296 by 10 to the 27 joules. It's a lot of energy. Okay, number 6 is a little bit more involved. We've got an example of a fusion reaction. So 2 deuterium nuclei that will combine together to form a helium nucleus. Okay, so the things that react together, they're the reactants. And the thing that you get made or produced is the product. Okay, well, our first step is let's get the masses of each of these. Well, the mass of each deuterium nucleus is 3.344 by 10 to the minus 27 kg. And we've got 2 of them. So the total mass of the reactants is 6.688 by 10 to the minus 27 kgs. That's the mass of the reactants. Cover that for a moment. Versus the mass of the products. In this case, there's only one product. The mass of the product was 6.646 by 10 to the minus 27. Okay, so straight away from looking at that and just doing a kind of a common sense check, the mass of the products is less than the mass of the reactants. This is bigger than this. That means that energy is being released in this reaction. That makes sense. That's what we're told. So let's see how much energy. Well, to calculate how much energy is released, we're going to use E equals mc squared. But first we need to see how much mass was converted. So it's the difference between the products and the reactants. So let's take our 6.688 by 10 to the minus 27 kg and subtract the mass of the products that we got, which is 6.646 by 10 to the minus 27 kg, meaning the total mass that was transferred or converted to energy was 0.042 by 10 to the minus 27 kg. Okay, so now we know how much mass was converted. Let's use E equals mc squared to figure out how much energy that would yield. Okay, so the energy is the mass, which is 0.042 by 10 to the minus 27 kg, multiplied by c squared, which is 3.00 by 10 to the 8 meters per second. And don't forget that's squared. Again, I've ran the numbers just to speed things up a little bit. That gave me 37.8 by 10 to the minus 13 joules, or just to get it in the scientific notation with the first digit between 1 and 10, 3.78 by 10 to the minus 12. Okay, have a go at 7 to 9, and remember, avoid 10.